Liquid in a shape problem. That's about as bad a name I think I could categorize it, so I apologize for that. But what's going to happen is we're going to have different shapes, and we're going to pour liquids into them, and because the shapes don't stay the same, the liquid that goes into them, things change. Like for example in this one, we've got a trough 10 feet long, and the ends are isosceles triangles. So if you don't know what a trough is, here is an isosceles triangle. And so it is something that could hold water. We're going to pour water into this. Okay? It has an altitude. Altitude is another word for height. An altitude of 3 and a base of 4. And this is 10 feet long. So there's the picture of our trough. And one of the things that you're going to find in these questions is the ability to draw a picture is going to be important. If water is poured into the trough at a rate of 3 cubic feet per minute, how fast is the water level rising when the water is 1 foot deep? So if we think about this just holistically, as you pour in water, the height is coming up fast at the beginning because it's so narrow at the bottom. But as time goes on, it's going to raise slower and slower and slower. Can you see that? Can you imagine that? Okay. So now, when it's 1 foot deep, how fast is it rising? That's what we're going to try to figure out. So we've got to set things up again. Do our initial setup. What do we know? We know that the volume, we're told dV dt, it's getting poured in 3 cubic feet per minute. So that tells us that volume is a function of time. How fast is the water rising? We want to find dH dt. When do we want to find dH dt? We want to find dH dt at h equals 1. So that tells us that height is a function of time. Cubic feet. Yeah, if you want to do feet cubed. No, cubic feet cubed. Whoa. That hurts the brain just a little bit. Yeah, just think about it a little bit longer and you will lose a little bit more brain cells. So, what is our volume formula for our trough? Well, our trough is a triangular prism. Okay? Our trough is a triangular prism, so we need to figure out how to figure that. The area of your triangle times by your height will be your volume.
Base times height divided by 2.
Okay? So base times height divided by 2 times by the length. And our length is constant here. Our length is always 10 feet. So our volume, yes, the base is changing too. So our volume is our triangle, base times height, divided by 2, times by the length of our trough, which happens to be 10. Now, we have a problem here because we've got an extra variable. We've got our base. So we need to figure out a way to relate our base to our height. Our base is always going to be, now let's look at that triangle off to the side here. So we know that when it's completely full, the altitude was 3, and your base here is 4. Okay? Now, no matter, we don't know where our water level will be, but wherever our water level is, this is the height, and this is the base. And so we can use ratios to look at this. We know that this ratio of our base divided by our height has to be equal to the larger similar triangle, which is 4/3. Does that make sense? If I do a ratio of my base to my height, it has to be equal to 4/3. Now what that allows me to do is it allows me to solve for my base and get that my base is 4/3 my height. I can now plug that into my formula here, where the base is, I can write 4/3 height times height divided by 2 times 10, which I'm just going to go times by 5. Simplifying this, we now have our volume formula to be 20/3 h squared. And now we have an equation that's relating our volume to our height. Both of those are functions of time. So we can take the derivative with respect to time. So dv dt will equal 40/3h dh dt. And what are we trying to find? We're trying to find the rate at which the height is changing when the height is 1 and the volume is being poured in at a rate of 3 cubic feet. So this is 3. This is 1. And to put our units in there, we were dealing with feet per minute. Yeah. Yes. Because you're trying to find. What's that? He's saying, why can't we plug in h equals 1 earlier? Or when do we plug in h equals 1? Well, when you're trying to find dh dt at a certain time, you have to plug it in into a formula that has the dh dt. If you plugged it in at the beginning, you just get a constant volume at that moment. You wouldn't find any kind of rates. You would just have, if I plug in 1 right away, I can find the actual volume when the height is 1, right? So if I plug in 1 here, I find out that my volume is 20/3 feet cubed. That's my volume. But it doesn't tell me how, it's not telling me how fast it's rising at that point. It's just giving a snapshot of that's the volume. But now that we figured this out, we can say that 9/40ths of a foot, whew, that's how much we can expect it to, that's how fast it's rising if it continued at that rate.
Make sure you take it out before.
For it, yes. Okay? So now we have same liquid in a problem, but now it's a cone. So I want you to think about pouring into a cone.
We like cones in this class.
Well, we don't want to have too many crazy formulas.
I agree.
Gonna get some scrap paper. Pencil. Check your results. So there's our cone. Volume is a function of time, h is a function of time. I set up my volume formula for my cone. Then off to the side here with the blue, I set up ratios for the radius and the height. And your radius is equal to 3/5 your height. That gets substituted back in.
These ain't great. The ones where it's like, oh, nicely fill it, like make a little small cone get bigger is nice. This ain't great.
Not the biggest fan, but that's probably taller than what you said I did. Oh, yeah, it's a French one.
Okay? Mine technically should still be right even though I have the wrong answer. I like that. That's confidence.
Ramsey is so confident.
I think calculating it, man. It's only 9 pot.
Yeah, go ahead.
Okay.
We're not talking about this. I could have just simplified it more.
That ain't the height we're looking at. Why? Because we didn't fill the whole thing up. Oh, goodness me.
Any questions about any parts of it?
Not yet.
Not yet. I mean,
Number I saw and I assumed.
again, start with your formula. Don't worry about trying to get the variables. And then using your ratios, I find really helpful off to the side, drawing the picture